Okay, so now I'm going to talk about, today I'm going to talk about the kind of classical local Langlands correspondence. Of course, people are still actively working on this side, and it seems a bit strange to call it classical, but ancient. Okay, but actually this, so firstly, this will be used in several places. So it will be used in Linus's talk later this week, and then it's also used fundamentally in Hamann next week. So this is an important part of even the categorical story. So we'll take F to be a p-adic group, field. And G over F to be quasi-split. And again, we'll take like coefficients of say like representations and L groups to be C. Okay. And then I want to define capital phi G to be the set of Bertoloni parameters of the L group of G. And actually, I'm going to assume that they're Frobenius semisimple. So this is one place that the classical picture differs from the categorical one. And I guess we more or less know what all this notation means by now from David Helm's talk, but is there something I need to define?
Probably Frobenius semi-simplicity, because I ignored it.
Yeah, so I mean, you can just pick some choice of Frobenius, and this will be some element in G hat, and okay, it will be some element in G hat cross like Frobenius, and then you can project to G hat, and then you want that this thing is semi-simple. It's conjugacy classes, yeah. Yeah, so there's another formulation where you can instead take the Weil group times SL2, and there's kind of a well-known translation between these two pictures. So as David mentioned yesterday, like this, when you try to consider a moduli space of these W cross SL2 parameters, it's really disconnected. This Bertoloni one, at least with coefficients in C, gives kind of the correct moduli problem. But that one is a natural thing to consider, and it will kind of show up a little bit in this talk.
So for you, WG means the Weil group semi-direct GA? Or
Yeah. Okay. And, okay, so what is the statement? So a lot of times when people give these kind of talks, they ease you into it by talking about GLN. Well, I'm not going to do that. So so you have to fix a Whittaker datum. B phi. So B is a Borel, and phi is a non-degenerate character of the unipotent radical. Non-degenerate means that it doesn't vanish on the like simple root vectors. I guess really you can consider these things up to equivalence. So I'll call this omega, and then the claim is what? But it could be 0 in some places, right? Can't it? No. All right, fine. Then there exists a natural bijection depending on this choice of Whittaker datum. oh, I skipped a step. So I want to define SV to be the centralizer in G hat of the image of phi. And I want to define SV bar to be SV mod CG hat gamma F. So gamma F is the Galois group, absolute Galois group of F. Okay, and so then we should have pairs phi and rho such that phi is one of these Frobenius semisimple parameters, and rho is in and then rho is a representation of the component group of this S, an irreducible representation of the component group of this S phi bar. So, so some people like to say that like this pair, so a given pi will map to phi pi and rho pi, and like the phi pi is like the family name of pi, and the rho pi is like the given name.
I think WeTech guy introduced this.
Is it WeTech? I've heard Tasha say this a lot too, but okay. We can attribute this to WeTech. Okay. So this is kind of the picture, that you should have some bijection like this. And you would want to say that it's like canonical in some sense, but that's actually quite a subtle question if you're just looking at a bijection of sets. So a lot of people have thought about this question in the classical setting, but so I'm not really going to focus on the canonicity. One reason is in the categorical picture, like it's actually kind of straightforward to say what canonical means. So this kind of resolves this problem. And the second thing is that it's going to lead us a bit afield. But what I do want to talk about is what properties we expect this bijection to satisfy. So the first one is just implied by what I've written, is that for a given parameter phi, we can define this L packet, which will be the pi's such that phi pi equals phi. And this is finite. Because this component group is some finite group, so it only has finitely many irreducible representations. Okay, but already this is, in this Fargues-Scholze construction that will be discussed later, this is already like, highly non-obvious and not even known. So the next thing I want to say is, so certain nice kinds of representations are known to have nice kinds of first and last names. So if pi is discrete series, then that should be the same thing as phi pi doesn't factor through proper levy. Yeah. Because we're using this Bertoloni thing, I think I really have to say levy instead of parabolic. And then this is the same thing as S phi bar is finite. So, and it turns out, related to what Wansu was saying, so it turns out that in the discrete case, the centralizer of the Bertolini parameter is going to be the same as the centralizer of the SL2 parameter. So in general, that won't be true. In general, my centralizer doesn't have to be a disconnected reductive group. It could have some unipotent part, but at least in the discrete case, they're the same. Okay. And the next thing is compatibility with parabolic induction. So we'll define the semi-simplification of phi is just a restriction to the Weil group. And then if P is in this normalized parabolic induction, then what should be true is that the semi-simple parameter attached to pi is the same thing as this composition, where IM is like the inclusion of the Levy, the L group of the Levy into the L group of G. So Levy subgroup up to maybe a choice of a Borel of G and of G hat. The Levy subgroup is determined by some subset of the simple roots, and so this determines some like embedding. When you have like, if you want to consider L maps of something that's not a Levy, then this gets a lot more complicated. But in this case, it's simple. Okay, questions so far?
I have a question.
Yeah.
How does the Whittaker datum come in here? Or did you say?
So I didn't really say, so, right, but that's a good question. So the Whittaker datum will not affect the family name, but it will affect the given name. It will affect the row pi. And a lot of the properties that I've discussed so far, like being discrete, turn out to not care about the row. So there's an observation here, like property 2 implies that if your L parameter is discrete, then everything in the packet has to be a discrete series. And conversely, if there's a single discrete series in your L packet, then actually the whole thing, and then everything in the L packet is discrete. But we'll see there's some properties where this is not the case, like for supercuspitals. Okay. So then we can ask that pi is omega generic, and this means that Homs from the unipotent radical, so pi restricted to this unipotent radical into this phi coming from our Whittaker datum are non-zero. And this should be the same thing as phi pi has max possible monodromy. So what I mean by this is, so this phi pi is some Vedolin parameter. So it has the Ve part and then this Delin part, which is some nilpotent element in the image of this GA. And there's, given the Ve part, the Delin part could be, it could be trivial or it could be some big thing. And this is saying that it's as big as it could possibly be given the Ve part. And maybe...
But you also need that the given name is trivial.
Yeah, I'm working on it. Yeah, okay. Okay, and then, fine. So I'll deal with the attributions in a second and make Dave happy first. That's our priority here. And then this should be equivalent to like this parameter is smooth in par G tilde. And then also you need that the given name is trivial. So this is an example where this really matters. And that's why I called it omega generic, because it really depends on the Whittaker datum. So I guess...
Clarify the logic, though. You've written, I see some if and only ifs, and then I see a plus.
So, yeah, so on the left-hand side, we have this generic condition, and then it's equivalent to two things. In both cases, you need that rho pi is trivial. So we're just gonna, that will always have to be true. And then there's also a condition on the parameter, and that is that it has this maximum possible monodromy. And I'm claiming that that is equivalent to being a smooth point. So I guess there's this Dot Helm, Kernchuk Moss, their second paper, this like local Langlands and families of Banal case. So they kind of heavily discuss this, and then maybe I'll also, for this first equivalence, maybe I'll also mention this paper of Cunningham, Dijals, Fiore, and Jean. Okay. So then I thought about this a little bit, about whether I would include this. So you can ask for pi to be tempered, which is like square integral plus epsilon. So the relationship with temperedness in the categorical Langlands program is kind of a tricky one, because as we'll see, this definition really depends on the topology. So it's not like such a natural notion. On the other hand, classically, like the way that this Langlands correspondences are constructed is they are kind of constructed from the tempered representations. There's this Langlands classification. And so they played a really integral role. So I think it's worth mentioning. So this condition is the same thing as the okay, I hope I'm not messing up here. The restriction to the very part is bounded. Mod center.
Tempered really means tempered. You don't even have to say.
Yeah, okay, essentially tempered. No, this isn't quite right? I have to do this like twisted restriction, don't I? Like, otherwise, like Steinberg and trivial have the same. Steinberg should be tempered. Okay, this is the so this restriction should be if you consider it as a W cross SL2 parameter. Wansu's revenge. Okay. All right, and in the tempered case, so if phi is tempered, okay, maybe so if phi is tempered, then there's such a thing as there's a character, a distribution character, where we sum over the packet, and then we weight it by the dimension of rho pi. And so this theta pi is like this distribution character for representation. And so we can form this thing, and this should be a stable distribution. And furthermore, we can construct these non-stable distributions. So we're scaling by the trace of rho pi at some s, where s is in s. So let's say s is in SV lifting some S bar in SV bar. Okay, and then the other statement is that I want to make is that the set of these phi S phis ranging over representatives of this like pi 0 SV bar is a basis for the span of these theta pi's. So this is, so if you take the span of these theta pi's, then the theta pi distributions themselves give you some basis. And what I'm saying is there's some kind of dual basis coming from these choices, from these like weightings in this way. Okay. And then maybe one of the most useful properties is this endoscopic character identity. Okay, maybe I should say I've been listing a lot of properties. Are there any questions? Okay. So yeah, so this is a bit technical to state completely precisely, so I might cut some corners here. But an endoscopic datum is going to be some triple of data. So this is an endoscopic datum for G. And so eta will be a map from, so H will be some F group, quasi-split, and eta will be a map from LH to LG. And S will be in G hat such that the centralizer, the connected centralizer is like eta of H hat. Okay, so the setup for this endoscopic character identity is that you have some group G and then you have some auxiliary group H. And G and H don't have to be themselves related, but their dual groups or their L groups are related by some embedding eta. Okay, yeah, eta should be an embedding, I guess. Okay, and then the final piece of information that we need is some parameter phi H of H such that maybe n phi of phi G such that eta composes phi H is phi. And then, okay. So why do we care about this endoscopic situation? Well, it turns out that given a distribution on H, there's some mechanism to transfer that distribution to G. And so this transfer, and so what is then true is that the transfer of the stable character of phi H to G is going to be the S-twisted character of phi. So okay, I don't really want to go through how we transfer these distributions that much, but basically, like, if you have some function f, a function of G, then you can cook up some auxiliary function fh, a function of h, and then the transfer of this stable distribution of phi h to G is this S-twisted thing, says that will be some equality like this. So evaluating these distributions of these functions. And so practically this is very useful because it allows us to transfer information about these distributions on G to some Levy's or some endoscopic group H that will probably be smaller than G. And so this sets up the possibility to do a lot of like inductive arguments. And in fact, this endoscopic character identity is kind of crucial to how like these classical local Langlands correspondences have been constructed in many cases. So typically what happens is that, yeah, so H is kind of smaller, like, is smaller than, G, and also this pi of phi h is going to be smaller than that doesn't make any sense. Smaller than pi phi, and one other piece of information is that if you have some s in pi 0 SV bar that is not trivial, then there exists, so let's say S bar, then there exists an endoscopic datum HS eta where S is going to be a lift of our S bar, non-trivial, and phi h such that phi is equivalent to eta composed with phi h.
Can you say a bit more about what you mean by smaller?
So the second thing is these are finite sets. I think set theoretically it's like maybe always smaller, or it could be equal, but I think it's typically smaller. And I think it should be always smaller. And then the first thing, well, the dual group of H is embedding into the dual group of G. So like as the dimension of a group, it has shrunk. And I should say even, so this endoscopy is useful even for like discrete parameters. So in this discrete parameter case, the parameter does not factor through a levy, but it could factor through an endoscopic group. So this endoscopy is useful even for these discrete parameters. Yeah. There's also a notion of twisted endoscopy. I'm not going to discuss that, but it is also useful. You can just believe me. Okay. And now I want to say some of what is known, like when do we actually have such constructions? Probably I will mess up some citations here, so feel free to let me know. I'm not going to say everything that everyone has proven. I think we would be here for a while. But the GLN case was proven by Harris-Taylor in 2001, and also NER in 2000. So one remark is that the GLN case is kind of, a lot of times people start with that case because in the GLN case, these L packets are singletons. And so the whole picture becomes a lot simpler. So how did this, like, for instance, how would this Harris-Taylor construction work? Well, I'm not going to give you the full details, but one thing is, firstly, you can reduce to the, so something that is known is that you can reduce to the supercuspidal case. So you really just have to construct this thing for supercuspidals, and then there's some machinery that builds it out for everything else. And so then Harris and Taylor used the cohomology of local and global Shamar varieties to kind of make this construction for supercuspidals. And that kind of like, that gave them a lot of other things, like sort of there's some local global compatibility, for instance, like built in to their construction because it comes from a geometric place. And then, so for a lot of classical groups like sp2n, SO2n plus 1, and SO2n with an asterisk that I guess has now been removed by Hao Peng. So maybe I'll attribute this to Arthur's book, 2013. And then finally, the unitary case mock, kind of using the methods or adapting the methods of Arthur to the unitary case. And so these cases, they kind of build off the GLN case using endoscopy and twisted endoscopy and like this intertwiner relation, Well, you should ask Scholze, actually, if you have questions about this. He once told me, I was a grad student, and I was like, I'm going to read all of Arthur's book line by line, let's go. And I asked Scholze, and he said, you don't need to know how the sausage is made. So I defer to Scholze on the sausage manufacturing. Right, that's true. Yeah, they contributed a lot to this picture. Yeah, let me maybe leave it here before I make a lot of miscitations. Okay. But just to say that at least for classical groups, we kind of know everything for a lot of these examples. One comment I will make is that these classical constructions are a little bit like, maybe I'll say like inflexible in a certain sense, which is that you might think that, okay, if you know it for sp2n, you know it for inner twists of sp2n or something like that. But actually that's really hard. Like it turns out like that kind of adaptation is really difficult. And you might think that you know it for sp2n, so you know it for gsp2n, but that also is really difficult. So you might think that like, I just read a couple of groups, and then for like various central extensions and things, it's like easy, but that's not actually true. So that's maybe one warning. But okay, I wanted to do an extended example here. And I wanted to talk about parameters of classical groups, so we can actually see what these things look like a bit. And in particular, I wanted to, so these are like these groups that I've listed above, but I wanted to focus on, let's say, G equals S of 2n plus 1. And I probably made some sign errors here, but so G hat should be sp2n, and this embeds via standard embedding into GL2n. And so that means that if we have some phi, a parameter of sp2n, sorry, of S of 2n plus 1, then we get some standard composed with phi, some parameter of GL2n. And in this case, it turns out that this parameter of GL2n completely determines the one we started with. For other groups, this is true, except for in the even orthogonal case. And in that case, or even special orthogonal case, it's determined up to like a factor of 2. Let's say up to some outer automorphism of the orthogonal group acting on the special orthogonal group. So that's related to this asterisk that I drew above. But okay. And so this, but what is true is this standard composed with phi preserves, I mean, this is a 2n dimensional representation that preserves some bilinear form. Hence will be self-dual. And that means that if standard composed with phi, we can write it kind of in its indecomposable factorization as like phi1 through, so these phi1 through phi k, these are indecomposable representations of some, representations of the Weil group, Wedeling group, then, right, then the point is that these have to group in a certain way. So on the one hand, if phi I is not self-dual, we can pair it off with its dual. Its dual will also have to show up since the whole thing is self-dual. And then And then everything else is self-dual, but there's actually a sign here. So let me try not to get this wrong. So what is this sign? So the sign of phi I, well, so if you have some representation M, then the self-duality, in particular, you'll preserve some pairing. So you'll get some isomorphism. You can write down some isomorphism with M and its dual, and then you can look at the dual of that. So then this will go from the double dual, which is isomorphic to M, to the dual again. And if you formulate this correctly, these two isomorphisms will differ by a sign. So that's kind of the sign I'm talking about. And so the first case is when the sign is positive, and the second one is where it's negative. And what will be true is that the reductive part of SV will look like the following thing. So these M's are, okay, there should be an MJ here, and these M's are just multiplicities that these given, so yeah, that these given parameters show up. So okay, so this is what the centralizer looks like. And remember that we're interested in component groups. So, but all these groups are connected except for the orthogonal piece. So this kind of non-trivial L packets or non-trivial component group is completely coming from this middle term that is controlled by these positive sign things. And so in particular, how could it be that phi is discrete? Well, we certainly need these sets to be empty. And we also need Mi is 1 for all I in I phi plus. And okay, right, so in that case, there's no symplectic or general linear part, and you just have O of 1, and O of 1, I guess, is like 2 points, just plus or minus 1. So then what happens is that this S phi, which turns out to be S phi red in this case, is just, okay, the groups are equal, but I'm discussing the size. So it will just be some, and in fact, the group is like Z mod 2 to some power. Okay, so this is kind of what happens, and this is why in a lot of examples, these L packets seem to be like powers of 2. Well, in the classical case, it's kind of forced by this computation. Questions?
S phi, but is it not S of standard composed phi?
No, actually, this is for S phi itself, I think. I mean, I hid some computation, but yeah.
Thanks, I get it.
Yeah. Other questions? Okay, fine. So, and so then the next question is like, well, suppose phi is discrete. When is pi supercapital? maybe I'll attribute this to Langlands. So pi as above. Then there's actually kind of a really nice like combinatorial formula for exactly when. So the family name has to be a discrete parameter to get a supercuspidal, because supercuspidal representations are automatically discrete. But then there's some extra, the given name also has to have some very precise property. So let's see what that is. So first of all, phi pi has no gaps. So that means that if sigma times n, so this is like some n-dimensional representation of GA, appears in the indecomposable pieces of standard composed with phi, then so does this guy, at least for n greater than 2. And so this means that your parameter will have these like descending chains of like sigma times n minus 2, sigma times n minus 4, and so on. And then rho pi is alternating. And okay, so the point is like each of these indecomposable factors for a discrete parameter contributes a z mod 2 coming from this O of 1. And so you can imagine that if you have some representation of the centralizer group, it's really for each z mod 2, you have to say what this representation does, and it will either be trivial or it will give you a sign there. So given that, the following makes sense. So I'm going to write, it's like if I write sigma times 2 equals -1, it just means that if you have a term like this, the sign has to be, of the non-trivial element in that z mod 2 has to be a -1. And also, this is the negative of this. So this second condition in particular is the alternating part. It says like as you go down this chain, you're flipping signs every time. And yeah, it turns out that if your phi pi and rho phi satisfies these conditions, then the corresponding pi is supercuspidal. This is kind of a pretty non-obvious and interesting fact.
Sorry, can you say a bit more about this sigma product n and how it's defined? Like what does it mean exactly?
So what I mean is that, so I was decomposing this standard composed with phi into some indecomposable factors. And what will any given indecomposable factor look like? You'll have an irreducible representation of the Weil group, and then you'll have some kind of representation of, some indecomposable representation of GA. But it, sigma is on the Weil group side, and the n is on the Deligne side. Yeah. In the SL2 picture, these just correspond to the irreducible representations of SL2. Okay. All right, so this was the end of my extended example, but I hope that this gives you some, if you haven't seen this before, I hope this gives you some intuition as to what these things actually look like for classical groups. And now I want to talk a little bit about inner twists. Because if you're thinking about categorical local Langlands, what I've outlined for you is maybe pretty far from the kind of picture that we're going to see. Like you could imagine that you're given categorical Langlands and you want to try to reconstruct this classical thing. It seems like what you would get is quite different to what I've written so far. So let me point out some differences. So on the automorphic side, so I guess we're not quite there, but Mingzhe discussed this Kotwitz set in her talk, and she hasn't discussed ISOC G and Bun G that extensively yet, but what we're going to see is that these groups GB show up kind of in the geometry of these stacks. And so you would maybe expect that we would actually be seeing representations of every GB, not just like the quasi-split G itself. And on the Galois side, in David Helm's talk, we saw this par G, and one thing that is true is if you have a parameter phi, then the classifying stack for S phi embeds there. So you might expect to see some kind of sheaves on this classifying stack. Like that's the kind of thing that could show up. But again, like in what I wrote above, that's not what was showing up. Rather, we were getting like representations of pi 0 S phi bar. So I want to try to like say something about, I should say, I don't think a completely finished, precise expectation of how classical and categorical local Langlands relate has been produced. I don't, like, generically, I think we have a pretty good understanding of what it should look like, but not for every parameter. But the first thing is that there's this formulation of Kotwitz, known in many cases. So roughly, this UN case is like Colette Minquez Shin White, and then SO2N should be like Chen Zhou, and SO2N plus 1 should be like Ishimoto. And so so what is this Kotwitz formulation? Well, it's a BG basic formulation. So on the left-hand side, we're taking representations now varying over this basic Kotwitz set. And this should be, and we're still fixing a Whittaker datum, and now this should be in bijection with, yeah. Yeah, maybe did I write that before? Okay, whatever, let's not think about it. Okay, and now rho is an irreducible representation of this S phi natural. And this S phi natural, this S phi natural is not so natural. It's the following thing. Okay, it's some group. But anyway, okay, this Kotwitz formulation, and so this is significant though because you're dealing with a whole ton of inner twists of G, and in particular I said that it's hard to extend LLC across inner twists a priori, so this is significant. Yeah? Yeah, the product seems a little bit suspicious. Thank you. Co-product. Okay, and then, right.
How do you read off the B from an object on the right side?
Yeah, that's a great question. So, yeah, thank you for that question, Jared. So, one thing we know is that this Kotwitz map, kappa, induces an isomorphism between BG basic and pi 1G gamma coinvariance, which is identified with ZG hat, characters of ZG hat gamma invariance. And there's a map from ZG hat gamma to this S phi natural. And so, given rho, we can take the central character, essentially, of rho, and this will be a character of ZG hat gamma. And
A bit of a vague question, but this seems to look like the compound packet of Vogan. Is there any compatibility between this and the compound packet?
right, so yeah, there is a compatibility. So the question was, oh yeah, I'm supposed to be repeating questions. So the question was like, this looks like a compound packet. How does it relate to this like compound packets of Vogan? So, okay. So these compound packets of Vogan, he works with pure interforms. And these are classified by just H1 of G. And, well, there's a natural map. And, okay, whatever, I won't draw the whole thing. But there's a natural map from H1 FG to BG basic. And the image is exactly the elements of BG basic that have trivial Newton map, trivial Newton point. And so that's kind of the connection, yeah. Okay.
You can also read it off as like the rows for which the central character is trivial on the identity component of the Galois character.
Yeah, that's right. It's yeah, so thank you. So you can, on the Galois side, you can read it off as the rows that are trivial on this like identity component of this ZG hat gamma. And actually, like, now that we see this picture that the central character corresponds to the ZG hat gamma, we see why we were taking this S phi bar before. We were quotienting by ZG hat gamma, but that was exactly forcing the central character to be trivial, and therefore, like, whatever rows we were getting had to be associated to G itself. So that's that connection. And then I guess so I'm sort of running out of time here, but one thing I want to mention is this paper with Masao Oi. And what it says is that if you have this Kottwitz LLC for G and levies, then you actually get so then you actually get some bijection like this, which is at least resolves the problems that I mentioned at the beginning of this discussion. So now we're seeing the full Kottwitz set BG, and now we're seeing irreducible representations of S phi instead of some other auxiliary group. So maybe assume. It's still not 100% clear how this formulation relates to categorical Langlands. And one reason for that is I'm still assuming, for instance, Frobenius semisimple everywhere. But of course, par G has these non-Frobenius semisimple points. And so the translation between this data and sheaves is not so obvious because of this, for instance. But at least this is a bit closer to what you might expect. And it seems to hold up well in some examples, for instance, in Dave's Beijing notes. Okay, so I think maybe I'll stop here rather than launching into anything.